Hi Chemistry, Mrs. KJ here going over 4.07 Thermochemical Equations. Chemical reactions propel our cars. Gasoline cars changed the world. The modern world was formed on the combustion of gasoline and oil. Gasoline-powered car engines contribute to global warming and pollution. All things gasoline involve the release of energy when gasoline burns. Here we will examine the concepts of various enthalpies of reaction and thermochemical equations in the context of alternatively fueled cars. Goals for this lesson: explain a thermochemical equation, explain how the physical state of reactants and products relates to a thermochemical equation, solve problems that involve heat flow and temperature change, define heat of solution. Thermochemical equations show reactants and products. Thermochemical equations can be endothermic. So remember, endo means take heat in. And if you notice, now they have another definition. It's a positive delta H. Thermochemical reactions can be exothermic, or they let heat out. And another way of saying that is it's a negative delta H. And you can get the study guide from slide 2. Gasoline-fueled cars release products into the air when burned. Cars burn gasoline to produce heat, which is used to do mechanical work, or in other words, make the car go. In theory, the more heat energy can be made, the more work can be done. So a fuel that produces the most heat energy would be ideal for an engine. However, not all of the heat energy does work. The conversion of heat energy to mechanical work is not 100% efficient. So in other words, all the energy that goes in does not come out as mechanical energy. And you can think of that too. I mean, we have to be able to hear the car. The car gives off heat that's not used to move it. Okay, so there's lots of basically wasted energy, and that's what this sentence is talking about. The conversion of heat energy to mechanical work is not 100% efficient. Some heat energy gets wasted. The wasted heat is vented by the exhaust system, along with noxious gases, and removed by the coolant system. Though essential to our way of life, cars emit greenhouse gases such as carbon dioxide. Furthermore, car emissions contribute to pollution such as smog and ground-level ozone. So atmospheric carbon has increased with industrialization. And so if we look at our carbon dioxide concentration in parts per million, they're using an ice core sample to find this out for getting data from the past. Actually, it's pretty amazing what they can get out of ice cores, like down in Antarctica or at the North Pole. It's amazing. And so anyway, so they show how it's at about 275, and then it's increasing starting here in the 1850s with more industrialization. And then once we hit 1950, their data, they're getting it from Mauna Loa, which is the Hawaiian volcano. And you can see a huge increase, which regardless of what people have as popular beliefs or not, I think we can all agree on the fact that when we use cars, pollution comes out of the exhaust, and that pollution has to go somewhere. Where does it go? It goes in the air. The biggest form of it is carbon dioxide. So when we're pumping that into the air, obviously, the air is going to have more of it. Gasoline combustion provides heat energy. Look at the combustion reaction of gasoline, C8H18. So we have 2 molecules of gasoline, C8H18 in liquid form, plus 25 molecules of oxygen gas. And what does that yield? 16 molecules of carbon dioxide gas, 18 molecules of liquid water. And look at the end here. We have something else. We have delta H equals negative 10,941 kilojoules. Okay, so we're going to talk about what that delta H is talking about. As written here, the chemical reaction is called a thermochemical equation. So thermochemical equation is a chemical equation that also shows the enthalpy of a chemical reaction. Like other chemical equations, thermochemical equations must be balanced. So that's when I read it, I made sure to talk about the 2, the 25. We had to balance it out. So on both sides, there are 50 oxygen. 18 of them are part of water on this side, and 32 of them are part of carbon dioxide. The states of all reactants and products are noted in parentheses. The change in enthalpy, or enthalpy of a reaction, is delta H, and that's written to the right. Delta H can be written in units of kilojoules or kilojoules per mole. If your delta H is negative, then we know that it was an exothermic reaction or heat was given off. If it was a positive delta H, then we know it was endothermic or heat was brought in. Remember, enthalpy is defined as the thermal energy content of a chemical system. The change in enthalpy, or delta H, is the change in thermal energy between the reactants and the products. So basically, a fancy way of saying, oh look, this is how much heat is being released. Change in enthalpy reaction. In any problem, you will either be given the enthalpy of the reaction or the information needed to calculate it. Typically, tables of enthalpies of various reactions can be found in chemistry textbooks, like that one online, the CRC Handbook of Chemistry and Physics, as well as Googling. The combustion of gasoline causes smog in large cities. All right, so let's go to our notes. I used the student guide to get our first paragraph, our goals, our keywords, and pronunciation. A thermochemical reaction is a chemical equation that also shows the enthalpy of a chemical reaction. And I'm just going to put in parentheses, basically, well, it's thermal energy or heat. Now let's just make it easy. Heat gained or lost during the chemical reaction. Okay, so it shows the enthalpy of the chemical reaction, which really is a fancy way of saying the heat gained or lost. And then I just copied this part of the slide because really it's very important that you know all the parts of the thermochemical equation, and it just lists them out right here. It tells you about endothermic and exothermic, and again what enthalpy is. So definitely not the most concise, but it's pretty well written. As always, feel free to modify your own notes. E85 cars burn a mixture of ethanol and gasoline. To reduce the amount of carbon dioxide, a greenhouse gas, emitted during combustion, new cars are being designed that can burn ethanol and gas mixtures such as E85, which is 80% ethanol, 15% gasoline. These cars are called E85 cars or flex fuel cars. Here's the thermochemical equation for ethanol combustion. So if we notice, we have ethanol as a liquid plus 3 oxygen gas molecules, and it forms only 2 carbon dioxides instead of 16, plus 3 waters, and our delta H, or our change in heat, is negative 2,434 kilojoules. Okay, so if it's negative, does that mean it's giving heat off or taking heat in? So if it's negative, it is exothermic, giving heat off. Again, note that the thermochemical equation is balanced and that the states of reactants and products are shown. So it's balanced. Check. We have liquid gas. Check. We have our change in enthalpy. Check. We have the fact that it's kilojoules. Check. So ethanol combustion is exothermic. Again, we know that because it's a negative delta H. Burning ethanol yields only 25% of the heat energy that burning gasoline does. Even though less heat energy is produced, E85 engines are more efficient, allowing them to produce the same amount of mechanical work. Burning ethanol also yields significantly less carbon dioxide than burning gasoline. This reduces greenhouse gas emissions, so E85 cars contribute less to global warming, or more importantly, contributing less to the greenhouse gases. Now, why do I say it that way? Some people have issues with global warming, which really should be called global climate change, because it's not that we get nice warm all the time. It's basically that you get icky weather most of the time. But the part that you cannot debate is the greenhouse effect. And the greenhouse effect is the fact of what happens with the carbon dioxide when we have it trapped in our atmosphere, which has always been the same. The fact of how that trend is changing right now is what some people like to debate. But the fact that greenhouse and greenhouse emissions and greenhouse gas effect exists is a fact. Other alternative fuels include liquid natural gases. Besides ethanol, alternative fuels can be liquid natural gases such as liquid methane, CH4, and liquid propane, C3H8. So we have our liquid methane plus oxygen gas yields 1 carbon dioxide molecule plus 2 water molecules. Notice we have our phases, and we have our delta H of negative 890 kilojoules per mole. If our delta H is negative, is it exo or endothermic? It's exothermic, or giving off heat. We also have liquid propane when added to 5 oxygen molecules produces 3 carbon dioxide gaseous molecules plus 4 liquid water molecules, and our delta H is negative 2,220 kilojoules per mole. And is that exo or endothermic? Exo. How do you know? It's a negative H value. Burning methane yields much less heat energy and carbon dioxide than any of the other fuels, gasoline, ethanol, or propane. The major problem with methane and propane vehicles is that these fuels are gases at room temperature, so the gases must be stored in a low pressure tank to keep them liquefied. So remember, we can use pressure to force those molecules together so close they become liquid. As the liquid fuel travels to the engine, it gets vaporized in a regulator or vaporizer, mixed with air, and burned in the engine. Most liquid natural gas cars were converted from gasoline engines, and many can use both fuels. These cars reduce greenhouse gas emissions and reduce the need for gasoline. So again, we have the name of our gasolines and the formula, and you can see the delta H value in combustion reactions, or what a huge difference in heat being given off. This table shows heat energy released by different types of fuel. Enthalpy of combustion. The thermochemical equations for the fuel reactions that you have seen so far all involve burning a substance completely with oxygen. This type of reaction is a combustion reaction, so combustion needs oxygen. So the enthalpy of reaction for the particular type of reaction is called the enthalpy of combustion, or the heat of combustion. And so what I added to our notes, when different fuels combust or burn completely with oxygen, different amounts of heat are given off. Here are some important notes about thermochemical reactions. Changes of state contribute to the change in enthalpy. When a reaction is reversible, so when you can have it go one direction and then have it go back the other way, the delta H of the reverse reaction has the same value as, but the opposite sign of, the forward reaction. So in other words, if let's say I could turn this around. Let's say I could make the carbon dioxide and the water turn into oxygen and the ethanol. Okay, so I had the arrow go to the left instead of to the right, so I was going backwards. Then the delta H would be positive 2,434 kilojoules. So when you do the reverse of a reaction, because you're going in the opposite direction, your delta H is the same number, it's just it has the opposite positive or negative sign. If you multiply a chemical equation by some factor, then you must also multiply the delta H by the same factor. For example, nitrogen gas plus hydrogen gas yields 2NH3 gas, and the delta H is negative 92.4 kilojoules. So let's say I multiply this by 3. So I have 3 times as much of a reaction. So I have 3 molecules of N2 plus 9 molecules of H2 gives me 6 molecules of NH3. And so it's 3 times as much. Well, guess what? As you kind of would have expected, it gives off 3 times as much heat. So if you take 92.4 times 3, you get the negative 277.2 kilojoules. Chemists determine most delta H under standardized conditions, so 100 kilopascals pressure and 0 degrees Celsius. Delta H under standard conditions has the symbol delta H with a O for a superscript. So the superscript on the H, sorry, it's a 0, not an O. It's a 0, showing that we're at STP, standard temperature and pressure. When hydrogen and oxygen combine to form water, they first form a water vapor. Then the water vapor condenses into liquid form. The changes of state contribute to the total heat released. So we have heat released from turning into gaseous water and more heat released from turning into liquid. The whole thing has this for a total, and we will continue in the next recording.